My name is Kazuki Shibanuma from Japan at the University of Tokyo. Today, I'm going to talk about the modeling of brittle crack propagation arrest behavior in steel plate. This slide shows the table of contents of this presentation. First, I'll explain the introduction of this study. And recently, the thickness of the steel plate used for the ship structure shows a rapid increasing due to the enlargement enlargement of the size of ship. It is known that increasing thickness of the plate makes a risk of brittle fracture initiation higher. So, arrest design for double integrity is important to ensure the safety of the ship structure. The arrestability of the steel plate is evaluated by a crack arrest test based on the linear fraction mechanics theory. There is two types of the arrest test, temperature gradient type and duplex type. And temperature gradient crack arrest test is used for the evaluation of arrest toughness KCA as a function of the temperature. On the other hand, the duplex crack arrest test is used for the clarification of the required KCA under the constant temperature for design of actual structures. This slide shows a procedure to evaluate the crack arrest toughness KCA obtained by temperature gradient test. In this test, crack is initiated at low temperature site by impact loading, and then crack propagates and is arrested at the high temperature site. Arrest toughness KCA is evaluated by arrest crack length and applied stress as this equation. And it is empirically known that the logarithm of KCA and inverse of the temperature shows a linear relationship as this figure. However, in the wide size duplex test, it has been reported that the crack was arrested even if stress intensity factor is larger than arrest toughness KCA. This theoretical background has not been clarified for more than 40 years. That is a long crack problem. And recently, however, the IAX published an actual design requirement of KCA as this expression. However, this design requirement is only based on the experimental results, so it is important to clarify the theoretical background of this long crack problem. It's important to ensure the safety of ship structures. That is the objective of this study. And then I'll explain the modeling of brittle crack propagation as behavior. This slide shows the concept of the proposed model. The brittle crack propagation and arrest behavior in steel plate is very complicated phenomenon. So I tried the simple modeling. This model is based on the fracture stress criterion, and we employed three assumptions for simplification. First is the shape of crack front is straight. Second is the side ligament have a crack closure effect. The third is the evaluation point is only at the mid thickness. And the brittle crack propagation and arrest behavior is simulated by solving the simultaneous equations of fracture condition, strain hardening, yield point, and dynamic stress intensity factor. And the feature of the model is one of the feature of the model is high-speed calculation. For example, it takes only few seconds for a standard temperature gradient type crack arrest test. In these following slides, we will explain the governing equations. First is the fracture conditions based on the fracture stress criterion. In this criterion, Non-linearity in the crack tip is modeled by fracture stress and the character distance, as shown in these figures. And the concept of the fracture stress is homogenization of the microscopic effects such as geometry, the spatial distribution, textures of microstructure, and so on. And the physical meaning of the fracture stress is a substitute the effective surface energy by linear fracture mechanics theory. Actually, we use the form of this equation for the fracture condition. The second equation is the strain hardening. We employ the general power hardening law as this equation. In the actual calculations, we use the tangent modulus form like this. The third equation is yield point. We employ the dependence of yield stress on temperature and strain rate. The final equation is the dynamic stress intensity factor. It is noted that in this equation, crack closure effect is considered in this equation. That is, the dynamic stress intensity factor is evaluated as a product of the correction factors of effective crack velocity and static stress intensity factor. Static stress intensity factor is calculated by the stress intensity factor by remote tensile stress minus crack closure effect by side ligament. A crack closure effect by side ligament is calculated by integration of the stress intensity factor by a point load at the surface of crack, like this. And the remaining program is the area of the side ligament. In the calculation of the area of the side ligaments, we employ two assumptions. First is the depth of the side ligament is proportional with the plastic zone size by linear fracture mechanics theory. And second is the dependence of crack velocity is divided by plastic strain obtained by finite element analysis. Consequently, the depth of the side ligament is formulated as this form. And brittle crack propagation and arrest behavior can be evaluated by repeated calculation of the simultaneous equation. And crack arrest can be predicted when the equation do not give any solutions. And to simulate the actual crack arrest test, fracture stress is required to identify beforehand. And I will show you the model validation. The first validation is application to the temperature gradient test. The specimen configuration is shown in this figure. And this table shows the specification of the test rates and test conditions. The focus of the test is the influence of the high applied stress. This graph shows the relationship between the KCA and temperature at the lowest 3 level of the applied stress condition. We can see these results fit the empirical curve. However, the highest level of the results of the highest level shows a deviation from the empirical curve. In addition, these photos show the fractured surface obtained by experimental results. We can see that the higher applied stress makes a deep side ligament like this. To simulate the test results, we identify the fracture stress like this. And the prediction results of the relationship between KCA and temperature are shown on this graph. You can see that the deviation of the experimental result from an empirical curve is successfully simulated by proposed model. And this figure shows the prediction results of the depth of side ligament. We can see predicted depths of side ligaments show good agreement with those of experimental ones. A second validation is application to the wide duplex test. This figure shows the configuration of the specimen. And this table shows the specification of the test plate and test condition. Focus of the test is long crack behavior under the condition of stress intensity factor is larger than arrest toughness KCA. These photos show the experimental results of fractured surfaces. You can see cracks are arrested even if stress intensity factor is larger than arrest toughness. And this graph shows the relationship between arrested crack lengths and temperatures of the experimental results. To predict these results, fracture stress is identified like this. And the predicted results of the depth of side ligament are shown on these photos. We can see the long crack behaviors are quantitatively explained by proposed model. And the prediction results of the arrested crack lengths with various temperature are shown in this graph. From these graphs, the crack behavior cannot be clearly distinguished propagation or arrest, but has a transition region, as this figure. Finally, I will conclude this presentation. In this study, we propose a modeling of brittle crack propagation and arrest behavior based on the local fracture criterion concerning crack closure effect by side ligament. In the model validation by comparison with the crack arrest test, the proposed model can reproduce the deviation of empirical curve of temperature and arrest toughness KC relationship under excessively high applied stress condition. And this model shows a possible solution of the long crack closure, where crack is arrested even stress intensity factor is larger than arrest toughness KC. The detail of this study can be found in the paper of the Indian fracture mechanics of this year. This is the end of presentation. Thank you very much.